this session, we will be discussing about the shear force and bending moment diagrams for cantilever beams with various load cases such as point loads, uniformly distributed loads, uniformly varying loads, and couple. Okay, moment couple. So like this, we'll see the cases one after the other. So the sign convention that is to be remembered while we deal with drawing of shear force and bending moment diagrams is the positive shear force is the one which is to the left of the section acting upwards and right of the section acting downwards is taken as positive. The forces which are acting downwards on the left side and upwards on the right side are considered negative shear forces. Similarly, the bending moment. The sign convention for bending moment is hogging moment is negative and sagging moment is positive. That means the forces upward on the left side or right side produce sagging moment. So that moment is considered positive, and the moment due to downward forces which produces hogging moment is considered negative. So let us consider the very simple case in a cantilever. The case of cantilever beam subjected to a single point load at the free end. So in cantilever beams, generally we consider the section and we consider the free end side of the section. Okay, left side or right side, it doesn't matter. We consider the free end side for calculating the shear force or bending moment. Okay, we sum up all the forces acting towards the free end side. Okay, to calculate shear force. Similarly, the moments of all the forces lying towards free end side for calculating bending moment. Okay, yeah. Coming to this, we consider the right side here because the free end is lying on the right side. So it is free end is taken as A and fixed end is taken as B. And there is a point load at free end W. Now we consider the section at a distance x from free end. Okay. Now what is the shear force at section x? Shear force at section x considering right hand side. The right hand side or left hand side, we consider the free end side. In this case, the free end is towards right, so we consider right hand side. If this is the case, if right end is fixed and left end is free, in that case, we consider free end side again. And we consider the left side this time. Okay, we consider the left side of the section here. Okay, for convenience, we will do that. For convenience sake, we consider the free end side. Okay, in cantilever for calculating shear force or bending moment. Yeah, now the shear force at x. Considering this, the shear force at x is right hand side we are considering. So we sum up all the forces. Algebraic sum will find all the forces towards right. So how many forces are there? Only one force that is acting downwards. Okay. So as per our convention, it is positive. So the convention for shear force, just now we have seen, left side upward and right side downward is considered positive. The forces acting upward on the left side of the section and downward on the right side of the section are considered positive. So the shear force here is positive. And if you observe, it is independent of x, so it is constant. Okay, that means the same section now is valid between the limits 0 to L. L is the span of the B. Okay, same section is valid between A and B. So the limits for x are from 0 to L. That means shear force at A, that is at x equal to 0, and shear force at B, that is at x equal to L, are same. At any other point in between also, the shear force is same, constant. Okay, it is independent of the position of the section. It is clear from this equation. Okay, understand? Similarly, we consider the bending moment at section x. Considering right hand side, the free hand side, here the force is downwards, so it produces downward bending, hogging moment, okay, with the concavity downwards. So this is negative bending moment, which is equal to force into distance. Okay, force into distance. Now bending moment is function of x. It depends on x. Understand? So at x equal to 0, bending moment at A, that is at x equal to 0, is 0. Similarly, at x equal to L, bending moment at B will be minus WL. Understand? It is clear. So the shear force diagram as shown here, but here it is considered negative. Our convention says it is positive. Okay, you can consider the other way also, it doesn't matter, but here in this case this is positive shear force. Understand? But bending moment convention is same, hogging is negative, so here it is taken as negative. 0 at A and WL at B. So you join the points because it is straight line variation, linear variation. The ends are sufficient to draw the line. Okay, yeah. This is the simplest case in case of cantilever, a point load acting at free. Okay, now you consider some other problem. UDL, uniformly distributed load acting over the span, acting over the entire span. So when UDL is acting, this is a B and this is A. Okay, span is L. So here also we consider one section between A and B with origin at free end. Here also we consider the free end side. Okay, with origin at A, free end. And this one section is sufficient. It covers total B. Okay, so the same section is valid between the ends A and B. Okay, so consider the shear force now at section X. What will be the shear force now? Considering right hand side, we have the intensity of loading as W per unit length. So W into X is the shear force. It is positive shear force. Right side downwards is positive. Our convention. Okay. So it depends on X if you observe. Okay. It depends on X. Understand? So here shear force at X equal to 0. At X equal to 0, the section will be at A. So shear force at A is 0. When X is 0 here, shear force at A will be 0. And when X equal to L, the shear force at B, okay, when x equal to L, the section will be at B. Okay, the section will be at B. So the shear force at B is W. Yeah. Okay. Now consider the bending moment at section X. Bending moment at section X. Yeah, what is the bending moment at section X? The moment of the force lying to the right of the section. So this is the load which is to the right of the section. This is the load. Okay. So the resultant of this load is equal to W into X. Total load on the right hand side of the section is intensity multiplied by the length X. Okay. And it acts at the middle. That means at X by 2 from the section. So the moment of the resultant from section is Wx into X by 2, which is negative. Because it is a hogging bending moment, it is negative. So it is Wx square by 2 minus Wx square by 2. So we get bending moment at A at x equal to 0 as 0, and bending moment at B at x equal to L as WL square by 2. But if you observe, the bending moment is a parabola. Bending moment curve is a parabola. It depends on x square. It varies as square of x. Okay. So it is a parabola. So when it is parabola, the curve, we cannot draw the curve with 2 points. With end points, we cannot draw the curve. So we find one more point in between, that is at the middle at x equal to L by 2 at C, midpoint of the beam. Okay. So at x equal to L by 2, what is the bending moment? It is minus WL square by 8. Minus WL square by 8. Okay. Yeah. Now we will plot the diagram. So for plotting the diagram, same thing. This we will draw upward because we consider the shear force as positive. So the shear force at A is at a fixed end B is WL. At A it is 0. So it is a straight line variation. Triangle. Okay. Yeah. Now, yeah, this convention is as per our convention, we will draw it upwards above the axis. Okay. Similarly, coming to bending moment, it is the same convention. 0 here and WL square by 2 at the fixed end. Maximum bending moment will be at fixed end. For a cantilever, yeah, these are all the conclusions. For a cantilever, the maximum bending moment will be at fixed end. Okay. Yeah. So these points are not sufficient, as I told you. So hence we have calculated the bending moment at midpoint. Bending moment at midpoint, which is WL square by 8. So if it is a triangle, then what is the ordinate at middle? If it is a triangle, if it is a straight line, the ordinate at middle will be half of this WL square by 2. Okay, it is WL square by 4. And if you see at C, the bending moment is WL square by 8. It says it is even less than the half of this. Okay, less than the half. Until it will be below this point. Okay, understand? This is WL square by 4. So it is less than this, means it lies towards this. Okay, somewhere here. Understand? So the curve will be drawn in this form. Actually, this is not to the scale. When it is drawn to the scale roughly, it will be something like, because this is WL square by 8, less than half. Okay, WL square by 4. If it is greater than half, then the curve will be something like this. At the middle, if the bending moment is greater than half, half into double L square by 4, half of this. Double L square by 4 country. If it is greater than that, then the curve will be something like this. But in this case, it is less than half, so it is to be drawn like this. Understand? Yeah. This is again a simple case of loading. Uniformly distributed load acting over the entire span of a cantilever. Understand? Yeah. Now we consider a partial load, UDL, acting over a part of the span, not entire span. It is acting over a part of the span of cantilever, and the length of UDL in this case is given as A, okay, and placed from free end, okay, to a distance A. So in this case, as usual, we consider the section here with origin at again free end, but this one section is not sufficient, okay, to cover entire span. This one section is not sufficient because the shear force equation which is calculated with respect to this section is not valid between C and B, okay. Between C and B, if you consider taking origin at free end again, okay, yeah, the equation for shear force or bending moment with respect to this section is not same with respect to this, okay, is not same as the shear force or bending moment with respect to the second section, okay, because the loading here is changing from C. Understand? There is no load between B and C, and there is UDL between A and C. So we need to consider two different sections between one between AC, that means in the portion AC, the other one between BC, okay, in the portion BC. So we need to consider two sections. So like this, wherever there is a change in load, we will add one section. Wherever there is a change in load, we will add one section. Okay? Understand? If there is a point load at some point here, then we may need to consider one more section. Okay? If there is some point load acting somewhere here, then we consider one more section because the equation for shear force and bending moment changes. Okay? And hence we have to consider separate section. For every change of loading, we consider a separate section. So now here we consider these portions separately. First, consider portion AC, and the limits for X are 0 to A. 0 to A. Okay, from A to C. X varies from or moves from A to C. Means the distance X varies from 0 to A. 0 to A. Understand? So now the remaining procedure is same. First we will find out the shear force at section X, which is Wx. Okay? Yeah. It depends on distance of section, position of section. Okay? So X is varying from 0 to A. So at shear force at section A is shear force at section A is at X equal to 0. It is 0. And shear force at section C, the shear force at C is, that means at X equal to A, it is WA. And also we have discussed in the previous cases, when there is no load between any 2 points, then the shear force remains constant. Okay, that means between B and C there is no load, so the shear force at C and shear force at B will be the same. Understand? So for now, we consider the bending moment also here in section AC, portion AC. So the bending moment at x is minus wx into x by 2, that is x square by 2, minus wx into x by 2. So it comes out to be minus wx square by 2. Okay. So now at x equal to 0, bending moment at A is 0, and at x equal to A, bending moment at C is minus WA square by 2. Okay, minus WA square by 2. And if you observe, the bending moment is parabola between AC. The bending moment is parabola between A and C. Now consider the portion BC. X varies from A to L. X varies from A to L. That means when X is A, the section will be at C. When X is L, the section will be at B. Okay. So the limits for X in portion BC are A to L. So now find shear force at X. So what is the shear force at X in this case, considering right hand section X in portion BC, considering right hand side? What is the total load on the right hand side? It is WA. WA, and positive because it is downwards on the right side. Okay. And it is independent of X. If you observe, this is independent of X. Okay. And bending moment at X is WA, the total UDL, into, it acts at the middle. Okay, from free end it acts at a distance of A by 2. Okay, and we are considering the distance of section from free end here. So what is the distance from the load to the section? X minus A by 2. X minus A by 2. Okay. And from this equation, it is clear that the bending moment varies linearly because x power 1 only we have. So it varies linearly. Understand? Yeah. Yes. So shear force at C and shear force at B are equal to WA. Because there is no load between B and C, the shear force remains constant. Similarly, coming to bending moment at C is, C means at x equal to A. So what is it? It is negative bending moment actually. You take it negative, minus WA into negative because it is hogging. Okay. Yeah. Minus WA into A minus A by 2. It is A by 2. So minus WA square by 2. Yeah, if you observe this, bending moment at C in portion AC and in portion BC are equal. Okay. Yeah, coming to bending moment at B, that is at x equal to L. At x equal to L, minus WA into L minus A by 2. Okay. This we will keep as it is. Now you plot the diagram. All this we plot above. Okay. Yeah. We plot this above actually. For our convention, it is positive. It is negative. No? So we take here WA and WA here. 0 to WA positive, and WA remains same between A and B and C. Understand? Similarly, coming to this bending moment diagram, it is same convention. So we know this point and this point, and the curve we have to draw between this parabola. So we find at midpoint, that means at x equal to a by 2, we find the bending moment, and we will get this less than half of this. So we will draw this curve like this. Okay, and from this, the variation is linear. Understand? It varies from minus WA square by 2 to minus WA into L minus A by 2. Is this clear? Yes. These are all simple cases. This is uniformly varying load. We will see this later. Yeah. Consider this case. Having several point loads, 4 point loads are acting. Okay, 4 point loads are acting at 0.5 meters spacing on the cantilever beam A, B, C, D. AE is the beam, B, C, D, and E are the load points where the loads are applied. Okay, A is fixed end and E is free end. So how many sections we need to consider here? For every change of loading, we need to consider one section. So we consider sections between DE, CD, BC, and AB. 4 sections we need to consider in total. Okay. Yeah, considering first section between DE, we find out bending moment and shear force. Shear force first we'll find. Shear force. Okay. That is for portion DE. For portion DE, section we are considering at a distance x from E. And for all the remaining sections also, we will take the origin at free end only. Origin at free end. For all these sections, we take origin at free end only. Okay. So here, for section between DE, what are the limits for x here? 0 to 0.5. Okay. X varies from 0 to 0.5. Okay. This section is valid between E and D only. Okay. Yeah. Shear force at x will be 500 newtons. Okay. 500 newtons. Downward it is positive. Right side downwards. So it is positive. And hence, as we know, the shear force remains same between D and E. Shear force at E and shear force at D remains same, that is 500. Because it is independent of x. Independent of x. And that is, there is no load, so shear force remains constant. We know that. We have already concluded. Okay. If there is no load between any 2 points, the shear force remains constant. And bending moment varies linearly between those 2 points. Okay. Bending moment varies linearly. What is the bending moment at section x? It is minus 500x. Negative because it is hogging. Okay. So now substituting the value of x0, we will get bending moment at E as 0. Okay. And bending moment at D as minus 250. Into 500 into 0.5 minus 250 units are Newton meters. Units are Newton meters. Load is in newtons and distance is in meters. Okay. This is for section between D and E. Same way, we consider the other sections and we will find the shear force. Okay. Yeah. So we can draw the shear force diagram directly. Just we'll draw the shear force diagram, bending moment diagram, in line with loading diagram. Actually, that will be easy to understand. Okay. So we generally draw the shear force and bending moment diagrams in line with the loading diagram. Okay. In line with loading diagram. So point A, point E, and here D, C, and B. Okay. So we have calculated now the shear force at E and shear force at D as 500. Okay. It is constant 500. So when you consider the section here, second section, what is the shear force at this section? Considering right hand side, free hand side, 800 plus 500. Both are downwards, so positive. 1300 total. Okay. And that remains same between D and C. So shear force at D and shear force at C are equal, 1300 newtons. And don't get confused here with shear force at D as 500 and shear force at D here is 1300. That difference is because when we consider this section at D, we consider this just to the right. Just to the right. Okay. And we are considering right hand side. So the load at D will not come into picture. Okay. This is for first section. We consider this section just to the right. And when we consider the second section, we consider the section at D just to the left, so that this load is also included. So when this load is included, considering right hand side, total shear force at this section will be 800 plus 500, that is 1300. Exactly at section D, now what happens? There will be a drop in the shear force by, this is 1300 and this is 500. So what is the drop in the value of shear force? That is 800, equal to the load applied at D. Okay. Understand? Similarly, the shear force at C, there will be a rise here from 1300 to 1600. Okay. And which remains constant between B and C. So the shear force remains constant between B and C. And at B, the shear force again rises by 400 and the shear force remains same between A and. So the shear force at A, when you consider right hand side, it is the sum of all these 4 point loads. Okay. 400 plus 300 plus 800 plus 500. Okay. Total is 2000 actually. Okay. Yeah. This is all positive shear force. This is all positive shear force. Similarly, bending moment diagram. Bending moment diagram is negative actually. What is the bending moment at X? Bending moment at X is minus 500 into X. Minus 500 into X. Okay. So bending moment at at E, that is at X equal to 0, it is 0. And bending moment at D will be 500 into 0.5, that is minus 250. Minus 250. Okay. So that means if you draw the bending moment diagram, so bending moment at D is minus 250, and here it is 0, and variation is linear. Similarly at C, if you consider, what is the bending moment at C? The variation is linear. So you calculate the bending moment at C considering right hand side. So 800 into 0.5, okay, bending moment at C is 800 into 0.5, this is negative bending moment actually, plus 500 into 1. So total is 400 plus 500, that is 900. Bending moment at C is 900. And what is the bending moment at B? 500 into 1.5, that is 750. 800 into 1, so 750 plus 800 plus 300 into 0.5, that is 150. So total is 900 plus 700, so 1700 total. 1700, okay. And at A, the sum of all these moments, you have to calculate that, okay. So what is the bending moment at A? This is bending moment at B, and bending moment at A is 500 into 2, that is 1000. 800 into 1.5, 1200. So 1000 plus 1200 plus 300 into 1, that is 300, plus 400 into 0.5, 200. So the total is 2200 plus 2700. This is 2000. This is 2700. Okay. The diagram is not to the scale, but it will be something like this. Okay. It consists of triangles and trapeziums. Triangles and trapeziums. Okay. So like this, when there is a series of loads, point loads are acting, we can easily draw the shear force and bending moment diagrams. Okay. Just shear force is obtained just by summing up all the forces. Similarly, the bending moment also. Okay. Yeah. With this, we end this session. We can continue in the next session.
Like, share and subscribe. Hit the bell icon for more updates.